Before we can talk about our increase of entropy principle, we have to define what an isolated system is. Let us consider a system, that is, a power plant as shown below within the red dashed line, and its surroundings, the environment, enclosed below within the blue dashed line, with our surroundings being large enough to consider any effect a change in our system may impart. In this instance, we can call this an isolated system. Now, recall, energy must be conserved. That is, whatever energy the system provides to the surroundings has to be equal to what the surroundings receives from the system. That is, we can say the change of energy for an isolated system is equal to 0. Or the change of energy of our system plus the change of energy of our surroundings is equal to 0. As our system rejects energy, our surroundings are going to pick up energy. The change of entropy of an isolated system can follow suit. That is, the change of entropy of our isolated system is equal to our energy transference associated with any heat transfer process plus our entropy production. Now, in this particular situation, if we look at our total isolated system, there is no transfer of energy between our surroundings to an additional surroundings. That is, delta Q per T is going to be equal to 0. Therefore, the change of entropy for an isolated system is going to be equal to our entropy production term, sigma. And we can express this as the entropy change of our system plus the entropy change of our surroundings being equal to sigma. This principle is known as the increase of entropy principle that states the sum of the change of entropy must be 0 or positive. And let us look at this in application. Say we have a 0.3 kilogram steel bar that's initially at 1200 Kelvin and it is cooled in a tank of water. The water has a mass of 9 kilograms and it's initially at a temperature of 300 Kelvin. Now this system can be assumed to be isolated. That is, the steel bar is going to transfer energy to our water and our water is going to accept this energy. Our water, however, will not transfer any other energy to the surroundings. If the final temperature of the bar water system is 303 Kelvin, we want to determine the change of entropy for the steel bar, the water, and the system. To begin, since we recognize that there is no heat transference between our system and our surroundings, we can employ our change of entropy equation. That is, the change of entropy of our metal plus the change of entropy of water is going to be equal to sigma, for there is no heat transfer between the water and additional surroundings. Now, since both of these materials are incompressible, we can express the change of entropy of our metal as the mass of the metal times the specific heat of our metal times the natural log of the final temperature of the metal per the initial temperature of the metal. And this will be plus the change of entropy for the water, which can be expressed as the mass of our water times the specific heat of our water times the natural log of the final temperature of our water per our initial temperature of the water. These two terms sum to sigma. And note that Tf is going to be the same. Substituting in values for specific heat and temperature, we have the change of entropy of our metal being equal to 0.3 kilograms times 0.42 kilojoule per kg K times the natural log of 303 per 1200 Kelvin. This would be plus the change of entropy for water, which would be 9 kilograms times 4.2 kilojoule per kg K times the natural log of 303 per 300 Kelvin. And this would be equal to sigma, our entropy production. When we calculate these terms, we see the entropy of our metal decreases, and by a quantity of 0.1743 kilojoule per K, whereas the entropy of our water increases by a quantity of 0.3761 kilojoule per K. Thus, our entropy produced is the sum of the change of entropy of our metal and our water, which has a value of 0.2027 kilojoule per K. We note the entropy of the steel has decreased, since its temperature has decreased, while the entropy of the water has increased, since its temperature has increased. And we see the increase of the entropy of the water outweighs that of the decrease of the steel. Thus, there is a net increase of entropy.